So, but onto a more precise thing. So we're talking about geostrophic adjustment today. And like I said before, this is one of the most important things we are going to talk about in terms of understanding how rapidly rotating stratified systems respond. So what did we talk about last time? Shallow water. And so we're going to do the geostrophic adjustment problem in the shallow water equations, but we could have done it in the full Navier-Stokes equations. It's just much more complicated mathematically, so we don't. We're just going to look at the shallow water one because that's enough to illustrate the important ideas. We could also do it in a lab tank, which in a sense we have. The video we watched with the dye and the stirred fluid is essentially a geostrophic adjustment problem. And so, or we could have done it in a numerical simulation. I'm actually going to show some numerical simulations of geostrophic adjustment. This one on the right-hand side is in fact one. We'll explain what that is. So geostrophic adjustment, in the simplest case, the shallow water equations in a quasi one-dimensional setting, the way that it's set up in Vallis, is a nice simple example to think about. But when we say geostrophic adjustment, it's not that specific one. It's the whole idea of an initial perturbation that sorts itself into a geostrophic part and an ageostrophic part. And what we want to get a handle on is how much geostrophic response there is and how much ageostrophic response there is, and like how to think about that. So from our perspective today, we're going to use energy and potential vorticity to think about that, and those are useful guiding principles. We're going to be studying a linear geostrophic adjustment problem rather than a nonlinear geostrophic adjustment problem because it makes it analytically tractable. But nonlinear geostrophic adjustment problems are easily studied in numerical models. I actually, if people wanted to play with it, I have a MATLAB code that does geostrophic adjustment in relatively elaborate configurations, which is what this little movie on the right-hand side is from. You can download that from my webpage. If you wanted to take that on as something you wanted to study for, say, the final project, that would be a cool thing to do. I think it's more elaborate. There's kind of, I have taught this class before based on computer models. And in that setting, we spent the whole time messing with this model, and that's why I wrote it, was kind of to get these pieces together. But this little model, it takes some hours to figure out how it works, which I don't think is extra time you all need to invest just to make yourself a movie. I can show you the movies, we can talk about it, and I can tell you some of the results without you having to get in there and fiddle with it, just because it's a little, whatever, you know. I don't know how many. So the big difference is there is no user manual for this code. The user manual for the code is go read the code. It's open source. You can figure out how it works by looking at what the equations are. That's the way that I think is a nice interaction, but among modelers. But I would say that that's not very typical between students. So normally you would get kind of a more gentle introduction to how things work. So okay, all right. So, shallow water equations. So last time we went bing, bing, bing. We're going to pick up here on the waves and geostrophic adjustment. Okay, oh, and actually we talked about energy but not PV. Let's go back to that point. Okay, so we did shallow water equations, solid bottom, reduced gravity shallow water equations. There's also multi-layer shallow water equations. The geostrophic adjustment system we're going to talk about could be done in either the solid bottom or reduced gravity. It doesn't look terribly different from a math perspective. The answers would be a little different. Okay, so we ended up talking about there is a potential energy, there is a kinetic energy, and you add them together and you get a total energy conservation for the shallow water system, and it's conserved globally, but there are these flux terms. There's an advection of potential, an advection of kinetic, and a pressure work term which looks exactly like the advection of potential, which is a little confusing. But same story that we saw in the Boussinesq equations, same story that we saw in the compressible equations. There are these flavors of energy. There's no internal energy here. Why not? It's effectively the same as an incompressible system, even though who was pointing out that it's an isomorphism of the compressible system? Was it you? We were talking about that after class. Another way to understand the shallow water equations is, interestingly, that it looks like two-dimensional compressible fluid dynamics. We can maybe come back to that later, but we don't need to dwell too much on the shallow water system. Okay, potential vorticity, though. We need to really get on our handle on this. We're going to talk. Potential vorticity is one of these concepts that the first time you see it in a GFD class, you think, that's the weirdest thing I've ever seen. That can't possibly be useful. And within a month or so, you find it very hard to express concepts without using potential vorticity. So it's really central to everything there is to do with geophysical fluid dynamics. And in some sense, it's the center of what Abby's thesis is on. So she's a good person to ask about how the subtleties of this. Okay, so normal fluid dynamics, we can make the vorticity, which is the curl of the three-dimensional velocity. So why is this a useful thing to do? Its average is 0, it's conserved. It's a nice thing to think about. One of the most straightforward ways to think about it is we can always write any velocity field as the curl of a stream function plus the gradient of a potential. This is the Helmholtz decomposition. If I take the curl of this, I only see this part because the curl of the gradient is 0. And if I take the divergence of the curl is 0, so I only see this part. So I can always write a velocity field as a part that's coming from the curl and a part that's coming from the divergence. And you can think about them separately. And in incompressible or Boussinesque fluids, which one is more important? The second term is not important at all because it's 0. This is 0 for incompressible or Boussinesque fluids because there is no divergence. So it's 0 over here too. So the vorticity is the only degree of freedom in a Boussinesque or incompressible fluid. If you know the vorticity, you actually know the total velocity. So that's one reason. So that and a conservation principle are the reasons why we care about vorticity. But vorticity is complicated, so how do we form the vorticity? Well, we basically take the curl of a momentum equation. Okay, here's one of the nasty things about vector calculus, which everybody skips over and people try not to think about too hard. But anyway, the curl works in 3D beautifully. It gives you a pseudo vector from a vector. In 2D, you can make something that is a curl, but it has only one component. So you take a 2D vector and you give yourself a pseudo scalar, which is in 4D, the curl operator takes a vector and gives you a second rank tensor. In 5D, the curl operator takes a vector and gives you a third rank tensor. So curl is a funny business. There's a simpler way to think about this, which we definitely are not going to go into. But the point is that the 2D form, really there's only one component we need to worry about, which is the vertical one. So you can use the right-hand rule for cyclones and anticyclones, and this vertical vorticity is all we need to worry about. So in shallow water systems, or things that have large aspect ratio, this is the vorticity we normally worry about. The one that's the vertical component. Interestingly, it's not always the largest component, which is maybe a topic for a different day. We'll come back to that when we get to turbulent flow. Okay, so how do I get an equation for the vorticity, either the 2D or 3D part? I just take the curl of the momentum equation and do a bunch of messing around. So if I take the curl of the time derivative part, I'll just get the time derivative of the curl because it'll commute. But this term, or the u dot grad term, and those guys get a little complicated. So normally we rewrite the momentum equation first before we take the curl to take advantage of that. And so the key rewriting is that u dot grad u goes into omega star in 2D, omega star cross u minus gradient of 1/2 u dot u. I write it as u dot u because it's important that it's a. So this one kind of looks like it makes sense, right? You take the gradient of u dot u, it looks like you're going to get u dot grad u. You actually don't. You get a funny curly bit, which is you get. This is not a simple thing. It has both a u component and a v component, and they kind of tangle up when you actually go through the process of taking x and y derivatives of u's and v's. So the simple one to think about is d dy of u. This is in the x component, but this is in the y component. So it's not going to obviously give you, u d dy of u kind of things necessarily. Okay? So that plus this equals this. So that's a calculus identity that we use to write the horizontal equation of motion like this. Why is this useful? What have we done by this term in particular? We make it into the energy part, and this is inside of a gradient. So this part has one part that can't be represented by a gradient, and one part that can be represented by a gradient. When I take the curl of this part vanishes. When I take the curl of this, it doesn't vanish. So essentially I'm playing this same game on this term and separating it into a part that will survive the curl and a part that gets squashed by the curl. So here's the part that's going to survive the curl. Here's the part that's going to get squashed by the curl. A beautiful symmetry, which you might have noticed already, is that omega star, the vertical component of the relative motion, and F are in the same operator. So why would you expect that? I could write it like this, in fact.
They have to be in the same direction because they need to be vertical.
They're both vertical rotations. One is from the planet, one is from the fluid. They should be very similar. The Coriolis force doesn't appear over here explicitly, but it's actually hiding inside of G because of the centrifugal force. So in some sense, we pulled the centrifugal part, hidden it in G. This is the Coriolis part. This is like the Coriolis part, the rotation cross U, the vortex force part of that. Okay? So now I take the curl of this equation. If I take the curl of this, I get the partial derivative of time with respect to the curl, so that's this guy. It's traditional to stick the F in here. I could stick an F in here for free. Why? It's constant in time. I need to be a little bit more careful in the advection term because the ddy of F is not necessarily 0. But if you're careful to think about taking the curl of these two and doing it out, you find that u dot grad u on these two terms is there. But there's a little bit left over. This part is also comes from these two terms. How do I know it comes from these two terms and not this term?
The curl of gradient is
curl gradient is 0. So this side doesn't contribute anything to the curl equation. But if I take the curl of these two, I get both an advection of this plus also this dot that. And look, it looks kind of nice, like it's a little bit like our continuity of mass equation where we've got a thing times a divergence plus the another part. But be careful, it's not. This is a vertical vector, not a scalar. This is a divergence of the horizontal velocity only. So it's not quite the same thing. Okay? So you have to be a little, like, there are some similarities, but Vallis goes through this more slowly, and some of the homeworks will start peering into different parts of this equation. Okay, but look at this equation and our thickness equation. Are they similar? And then the other one. Yes, they're really similar. In fact, maybe we like to cancel out this term with this term somehow if we could think of a way to do it. Does everybody see that? Because it would be really nice if we had something that was materially conserved, like salinity. Because the salinity marks the motion of the parcels as they move around. It would be really nice if we spend a lot of time thinking about potential temperature to do that with the temperature equation. Now, it would be nice to do that with the vorticity equation. Okay, so here's the trick. We take the ratio of this and this. So when we calculate ddt of this, we get a ddt of the top minus ddt of the bottom with a 1 over h squared part. And so the ddt of the top would have a term like this, but times 1 over h times that. ddt of h, what we really want is minus 1 over h squared ddt of h times zeta plus f. Does everybody see what I'm doing? Which would give us h 1 over h, gets rid of the minus sign, zeta plus f. Now look, this and this are the same but opposite in sign. So if I add this to this, which is just this equation, I get 0. Okay? I could just look at this original equation, I could just look at this equation and study this. But it's hard to think about because it turns out this term is actually one of the biggest terms in the equation. I could just study the thickness equation and not worry about this, but this term is one of the biggest terms in this equation because the convergence is really related to the height. The magical thing about potential vorticity is that the thing that's hard to think about here and the thing that's hard to think about here cancel each other out. And it's because of the ballerina. It's essentially like the ballerina vorticity thing. When you get taller, converge, your vorticity goes up, but so too does your thickness. And so they go up proportional to each other, so when I take their ratio, it doesn't do anything. When I get shorter, my vorticity goes down because I'm stretching out, but so too does the h. So the ballerina effect is described by the terms on this side and this side of those equations, and what we're doing is canceling out that effect by making the potential vorticity. Okay? Everybody have a sense of how that works? We're going to keep talking about potential vorticity for literally the rest of the semester. So this is not necessarily going to be obvious at the first pass. Okay, so we have potential vorticity. Let's talk a little bit about waves, and then we'll come to geostrophic adjustment quickly. Okay, so how do we find waves in equations of motion? You linearize the equations, and then you look for things that look like sines and cosines, basically. Or even more generally, you can look at things that look like a propagating function with a propagation in one direction or a propagation in the other direction. Like this is a propagation, as time goes up, x goes up in order to keep this constant. And then this is the same, but the other direction with speed, wave speed c. So I'll show you a movie in a second that explains this, but in the non-rotating case, we can drop the Coriolis terms, and this is what we get for our two shallow water equations of motion. We just get ddt equals the pressure gradient, ddt equals the pressure gradient, and then we get the thickness conservation, and in the linearized form, we just get the average thickness times the divergence, rather than the nonlinear product. And if I take ddt of this equation and ddt of this equation, I can cancel that out and just write this equation, which is, look, it's only got one variable. I've decoupled the eta and the u and v. I can get back u and v if I want to through this equation by going backwards. Or once I know eta, then I can find out u. Once I know eta, I can find out v. So I can go backwards. But this is a nice PDE for the single field of sea surface height variability. It has a spatial derivative, it has a temporal derivative, and for those of you who've seen wave equations before, this is a standard non-dispersive wave equation with speed square root GH. Okay? I could do exactly the same thing in the reduced gravity system. I would get exactly the same wave, except this would be square root G prime H. How do I interpret that?
The wave travels slower when the bottom is not solid.
Exactly. So if I have a total depth wave that's moving with a sea surface height, this is the equation. But if I have just the upper layer moving and it's expanding by pushing down the density jump and also lifting up the surface, it's an internal wave and it actually moves slower. So the shallow water equations in one layer and in reduced gravity versions actually give us both of those systems in the same math, which is kind of, that's why we did reduced gravity. Okay. So this is the general solution. So it has a rightward propagating part and a leftward propagating part. You can plug this into there and convince yourself that you do actually, with c equals square root of gh, you actually solve that for any function f.
Because of reduced gravity, will the eta dash will be higher for the lower thing or no?
The speed will be lower for reduced gravity.
But perturbations will get amplified?
The height will be bigger, and you can think about whether that makes the assumption of linearity break earlier too, which is an interesting question. But we had to linearize the equations to get a wave-like solution. So I wanted to show everybody a visualization of what a non-dispersive wave looks like. So this is a non-dispersive wave. Every wave number, every function in fact, travels at the same speed. So I put a very complicated initial condition in, and there is a leftward propagating part and a rightward propagating part. But look, they look exactly like the initial condition. They don't change. They just propagate away. Oh, and then there's an edge effect because I have used periodic boundary conditions, which is. So this is basically one half of the initial condition going this way, one half of the initial condition going that way. I could have put velocity initial conditions in. I didn't. I just dropped some sea surface height in and watched it propagate. This is what shallow water waves look like. So shallow water, H much, much less than L, are non-dispersive waves like this. Okay? And that's what this set of equations tells us. What if we keep a little bit of rotation? it's going to be a slightly different problem. It's actually a much more finicky mathematical problem if we don't throw away this term and the Coriolis terms. We still want to do a linearized system because we want waves. But the way you get at a solution is you assume a plane waveform e to the ikx minus omega t. So it has a spatial variation, like sines and cosines in x and y, and then a temporal variation with a particular frequency. And there will be a relationship between the wave omega over k will be equal to the speed of propagation, which is basically what this is telling you for a particular wave. And then we have a u part, a v part, and an eta part. And if you plug this into this system, you actually get a matrix equation for the evolution of those guys. Okay, and now we remind ourselves of some quick linear algebra. If a matrix times a vector equals 0, what can I say about the matrix if I want the vector to be non-zero? The determinant has to be 0. Why is that? Because if I could invert this matrix, I could write vector equals the inverse of whatever that is times 0, which is just 0. So I can't invert this matrix if I want a non-trivial solution. And the way I make a matrix that's not invertible is if I have a determinant that's equal to 0. Now I have a new constraint on these governing equations if I want this wave-like solution to exist, which is the determinant of this matrix. So I calculate the determinant of this matrix, and bing, that's it. This is the determinant of the matrix. And look, if I ignore this omega and this and set f to 0, hey, look, I'm back to something that looks like this. And in fact, if I ignore that and ignore that, I just get the non-rotating waves back. So the rotating waves are a little different because the frequency is offset by this f0 factor. And then there's also this overall omega factor. If this equals 0, how can I get there with that kind of a polynomial?
The frequency is not 0. So
The frequency could be 0.
Geostrophic current.
Yes. There are 3 roots to this equation. One root is the omega is a rightward traveling wave. One is that omega is a leftward traveling wave. And one is that omega equals 0, which is a steady geostrophic current. Omega equals 0 means neglect all the time derivatives, but hey, that's our geostrophic balance. So the geostrophic balance is hiding in the omega equals 0 root. Is everybody on board with how that works? Okay, and this is the just a plot of this dispersion relation. So here's the non-rotating case in the dashed, and then here's the rotating case, which is like this. So if omega if the wave number, is 0, then in the rotating case, omega is not 0, it's actually up here at f. If I set this to 0, those two balance each other. This is, for those of you who are, Brad Marston and colleagues wrote a paper about topological insulators in GFD a couple years ago, and it was in Nature. That's what they were talking about, the fact that this root of the waves are insulated when you add rotation into the system, which is kind of cool. Whatever. That's a whole other theoretical topic, which is nice. But anyway, okay. Here's a non-dispersive wave that we already saw. What does a dispersive wave look like? Why am I even talking about dispersive waves? Let's be clear. If this line is straight, it means that wave number and frequency are proportional to each other, which means wave number and frequency are proportional to each other, which means that C is not a function of K. For every omega, I get the same speed. So the wave is non-dispersive. If this is a curvy line, which it is in the rotating case, omega and k depend, their ratio depends, the slope is different here, from here, from here, from here. So there is a relationship between these two. So c is a function of wave number in that case, which means that some wave numbers are going to propagate faster than waves at other. So here's an example of a movie of a dispersive wave, same initial conditions. And what you'll see in this particular dispersion relation, the long waves get out ahead of the short waves. The long waves are faster than the short waves. Does that make sense? And there's also a magic other thing about group velocity and phase velocity, which means that the peaks travel at a different speed than the packets. Those are related to each other. But let's go back to, so which goes faster here, the long waves or the short waves? Wave number and frequency. So if the rate of change, so if c is the slope in this figure, c is the slope, it's right like this, so c is the slope, right? Which is faster, the big wave numbers or the little wave numbers? The big wave numbers are faster. So in the rotating case, these waves are a little slower as you approach the origin than the non-rotating case. Okay. They also are interesting in another way, which we'll see now. Okay, yeah.
I think the phase speed, for the phase speed, small wave number means higher phase speed, but it means lower group velocity.
Yes. So we're talking, the phase speed is like this. So c is the slope in a wave number to the omega, but d omega dk, the derivative, oh, this is also the slope, is the group velocity. This is the phase speed. So it's a little confusing. They are not independent. I guess I was thinking about this one.
Okay.
But yes, you should be careful between phase and group when they're not linear functions to distinguish the two. They both are slower in this case.
So I think the phase speed is faster for small wave.
All right, let's go back and think.
We can think of a line across the origin, and it rotates, and then we can see how.
Oh, you're right. No. At small k, omega is bigger for the same k. So you're right. The group speed is the slope. The phase speed is the magnitude of omega over at a given k. So it's an even weirder system. So, all right, for those who are wave aficionados, you can think more about these. I don't want to dwell too much on this. Okay, let's see what it looks like. So I have two categories of these movies. One that I call the plunger case, and one that's just like a drop of water. So and this is a plunger case, so I have a small plunger, which I'm just pushing the water up and down in the middle, forcing the sea surface height to go up and down. Since height is one of the variables in our shallow water system, it's going to drive waves. And you can see, as you'd expect, when this goes down, it sends out a low trough, like crest trough, crest trough. They're spreading out from that initial place. They're little tiny vectors that are showing the velocity direction. What would you expect the vectors to do? The velocity. It would be going like back in and out and in and out, because in order to raise the height or lower the height, you have to converge and diverge, right? But this is actually a rotating system, so it's doing something different than that. It's not just going in, out, it's spiraling in a cyclonic direction, because when it flows out, it feels the Coriolis force and it turns around. So this is a rotating surface gravity wave. which has both the Coriolis effect and the in and out of those shallow water waves. So it is a dispersive wave, which you can't easily see from this film, but if I had put it in wave number space, they would have separated out according to this kind of system. There would have been a group velocity, that would have been slower because the slope was slower, there would have been a phase velocity that would have been faster, so the crests and troughs would have propagated at a different speed than the packets in that system. So I could do this in a channel, and now we're looking at a slice through here. I'm doing it in a channel for a kind of interesting reason, but this is now a non-rotating wave in a channel. And as you'd expect, the waves propagate away, and there's velocities inside the waves. Kind of nice to think about that. Whatever. That one's just like, making a wave in your bathtub with a plunger. It just seems like the strange thing to do, but you could do it if you wanted to. This is where things start to get interesting. If we do the plunger case in a rotating channel, we have a broken symmetry. There's now a wave that travels along the wall, preferentially in only one direction. That's a Kelvin wave. So hiding in this set of equations are more kinds of waves than just the gravity waves, which is essentially saying that these other roots, these other pieces of this story are not zero. The Kelvin wave actually depends on both this root in one direction and this root in the other direction. Okay, now let's talk about geostrophic adjustment. Oh, Kelvin wave, if you put the plunger over near the wall, it only goes in one direction. You don't really affect the other wall. This is a super complicated scattering problem. But I could also just drop a blob of water and let it sit, rather than doing a plunger. So what's the difference between dropping a blob of water and the plunger?
The initial condition is just for one moment, then in the other phase it is going to be.
Exactly. And the difference from a wave perspective would be that when I use a plunger, I set the frequency of the wave to be whatever the frequency of the plunger is. When I drop the blob in, I'm introducing all frequencies. It's a Heaviside function, so its Fourier transform goes across all frequencies to some degree. Okay, so what do we find? We find at the beginning, boom, there goes a Kelvin wave, there goes a Kelvin wave, they're gravity waves. But then something's left behind. What's left behind? It's kind of a circular pattern. And if you can see the velocities, which I expect you can't, they're going around and around like this. What is that thing? It's an extra blob of water. Some of it runs away. Some of it's left behind. It has a high pressure anomaly. What's a stationary high pressure feature? A geostrophic flow. So I put extra water on top, and I could trigger a wave to run away, or I could form a geostrophic flow that remains. How much of each do I get? That's the question of geostrophic adjustment. The geostrophic adjustment is an anomaly at the initial condition. You let it settle out, let those waves propagate away, and then there's a geostrophic flow remaining at the end. How much of the initial anomaly ends up in the geostrophic flow is the geostrophic adjustment problem. So we know that when we get to the geostrophic balance, we're going to have a balance between the pressure force and the Coriolis force. So if it's a low, like this example, or a high, the opposite, we would have a circulating flow around it, which is just this equation we've already looked at. But what we don't know is when I put an initial blob of eta, and I still have the ddt, how much of the initial blob of eta goes away with the ddt in a wave, and how much stays behind. That's what geostrophic adjustment is. Okay, so we begin with the linearized shallow water equations. So linearized, keeping the Coriolis term. So here we've just thrown away the u dot grad u term, and here the u dot grad eta term is thrown away. So we have a linearized thickness equation and a linearized momentum equation. Here's the initial conditions. You can actually solve this under a lot of different initial conditions, but this is a nice simple one, which is positive anomaly all the way to the right side, negative anomaly all the way to the left side. So just a jump in surface height at the beginning. Not my ball drop, but like lift half the domain up, push half the domain down for the initial conditions. Let it go. What's going to happen? What would you guess would happen? What if it's a non-rotating case? What happens? The high stuff goes to the low side and fills it up. Propagates as a wave, and as that wave propagates, the taking stuff away and filling up the other side, the level on this side goes down. In fact, in the non-rotating case, throw this term away, we can solve it and we get exactly that. The leftward propagating and rightward propagating waves that flatten it out. It's just like half that interface goes this way and half goes this way, and as they propagate, they reduce the anomaly to zero. They travel at the gravity wave speed. Okay, so that's the non-rotating case. But in the rotating case, this is the non-rotating case. So the half the anomaly is propagating that way, half the anomaly is propagating that way, which is lowering from the initial anomaly down to zero, lowering from the initial anomaly up to zero. And this one is the velocity. When that wave is propagating, there's a little velocity right inside the wave, but there's not much velocity anywhere. There's zero velocity outside, so it's just propagating out. There's no velocity in the opposite direction. It's just spreading like this. Here's the rotating case. This does not look at all like that. There's this funny seesaw left behind. The velocity is smaller in the middle and peaked on the leading edge. This is that rotating gravity wave response. But also, it's going in 2D now. The wave's propagating this way, but you get flow in this direction because the Coriolis force is bending those velocities around as they're propagating out. And at the long time solution, what will this side look like? It'll be a flat surface. At the long time solution, what would this side look like? A geostrophic flow. We don't know exactly what it's going to be, but there should be one left behind. It has something to do with its curves. The relationship between sea surface height and v velocity and u velocity will have to be in geostrophic balance. And actually, since the sea surface height will be symmetric in this direction, this velocity will eventually go to zero, but this one will be preserved forever. So how do we do it? We go through this. How do we solve this system? Now this is a mess. In this case, you actually can write down the full solution and solve the whole problem with both the wave-like part and the geostrophic part, but that's not the way we normally do it. We take a trick, which is really pretty. We calculate the potential vorticity, and the linearized potential vorticity, which comes out of the linearized equations. We make the same game we just did over here, but we use the linear system, and we find the dynamics of potential vorticity look like this. Potential vorticity doesn't change in time. The advection term is gone because of the linearization. So whatever the potential vorticity are in the initial conditions are the potential vorticity at all times. Not true of the height because of that convergence term. Not true of the momentum because of the convergence terms. Not true of the vorticity because of the convergence terms. But the potential vorticity has just a clean zero sitting on the other side. And zeta plus f over h, when you linearize it, becomes like this. There's the zeta part standing alone, and the eta part is just multiplied by the constant part of the vorticity. So here's the initial conditions for sea surface height. Here's the initial conditions for potential vorticity, which looks, really similar to that. But at the final time, this is not going to be the final height distribution at all. This is going to be the final potential vorticity distribution. So all I need to do is take this and find a geostrophic flow that is consistent with that, which turns out to be these two equations. Actually, this is the solution to setting this constant, pushing it back through the momentum equation. So the velocity in the channel direction is 0 in the final state. The velocity in the other direction is not 0. It has this funny prefactor that goes like g eta over fl, x over ld, the magic ld, which we're going to talk about in a second, and that's exponentially decayed. So there's a profile that looks like this, away from the initial interface in the velocity. And the decay scale of this profile is LD, which is NH, oops, sorry, not in this case, G square root of GH over F naught. This is the deformation radius. It is the radius that the deformation of the rotating flow extends over. So we talked about the deformation radius just as being an interesting point where the effects of rotation and stratification were the same size. This is a much more interesting example where rotation is competing with the pressure gradients of the initial perturbation, and it settles out to a size where the pressure gradients and the rotation are happily the same size, and in fact that size is the size of the geostrophically adjusted region. Everybody understand what I mean here? There are a lot of pieces in this story. So the potential vorticity didn't change. The potential vorticity was there in the initial conditions, it was there in the final conditions. So the potential vorticity is the magic key to the geostrophically adjusted part of the initial conditions. If I knew the potential vorticity and the rest of it, the potential vorticity didn't change. So the potential vorticity was actually telling me about the underlying geostrophic adjustment even before the adjustment occurred. If I tracked just the motion of the potential vorticity, I would be tracking the geostrophically adjusted state. That's one lesson. Second lesson is that this deformation radius comes in and tells you about that. So how can I manipulate the deformation radius to make the amount of leftover geostrophically adjusted part weaker? How do I make this V smaller? I can make the layer thicker, which makes the deformation radius bigger, which makes the decay scale longer, but it also makes this coefficient smaller. So the thinking through how that works is something that's useful to do. From the perspective of the blob drop, I can tell you that if the blob is very, very small, most of the blob runs away as waves. If the blob is very, very large, much bigger than the deformation radius, most of the blob stays as a geostrophic anomaly. So just like the frequency part would sort, but if the plunger went fast, I get a lot of gravity waves and not much geostrophic response. If the plunger was very slow, I would get pretty much a geostrophic response all the time, because I would have time for the rotating part to catch up. If the blob is small, smaller than the deformation radius, I get mostly a non-rotating solution. If the blob is big, I get mostly a rotating solution.
So, when you say small, do you mean it is very small?
I mean large in horizontal scale. So it's a little complicated to look at this because this has potential energy on the top and this side is sort of kinetic energy. So to be more precise, what I should say is the fraction of potential energy in the initial conditions that ends up as geostrophic kinetic energy is different. For small scales, more of the potential energy is lost as ageostrophic kinetic energy. And when the scale is large, more of the initial potential energy ends up as geostrophic kinetic energy after the adjustment. And also geostrophic potential energy. So that's the way to think about it, is the energy budgets. It's a little hard from V to guess what the energies are, but that's the important part. All right, so we'll keep talking about this a little bit more on Friday, and we will go through the homeworks. We'll look at a lot of videos that show this stuff. But we'll focus on the homeworks for the upcoming week. So there's some homeworks on geostrophic adjustment, more stuff on chapter 3. You can take a look. We'll talk through those. And remember, the homeworks are due the following Friday, even though we're not having class next week. Okay?